Hello everyone, welcome to Jack's Computer Science YouTube channel. In this video, I'm going to start with Chapter 1, Information Representation. I believe you guys are now watching my videos through your tablet, or your mobile phone, or your laptop, and all of these three are an example of digital system. So digital system, it uses binary. Well, on the other hand, human beings, in our daily life, we use binary. Well, smart human beings, in order to give us an easier way to interpret binary numbers, we invent hexadecimal system. So today we are going to talk about denary, binary, and hexadecimal. So denary is a system that we are most familiarized. Imagine we have the following numbers, 3140, and each bit has its bit weight. So for the 0 bit, it has a bit weight of 10 to the power of 0, and 4 it has 10 to the power of 1, 1 it has a 10 to the power of 2, and the 3 has a bit weight of 10 to the power of 3. So we can also write this number as 3 times 1000, 1 times 100, 4 times 10, and 0 times 1. So denary is a base 10 number system, which all these indices has a base 10. So why do humans use denary and why computers use binary? Well, because for our humans, we have 10 fingers. However, the laptops, the computers are a bit silly. They only recognize low and high voltages. So it only has 0 and 1. That's the reason we call it binary. Binary is a type of base 2 number system. Base 2, which means that the bit weight has, instead of having 10, it will have 2. So imagine for this number, 101110, the bit weight of the right-hand side starts with 2 to the power of 0, which is 1, then 2 to the power of 1, which is 2, then 2 to the power of 2, which is 4, 8, 16, and 32, and so on. So now let's come to an interesting question. How can we convert a binary number into its corresponding denary? Well, the answer is very simple. We just multiply each bit with each bit weight. So for the left-hand side most bit, 1 times 32, we have 32. Then 0 times 16, we have 0. 1 times 8, we have 8. 1 times 4, we have 4. 1 times 2, we have 2. 0 times 1, we have 0. Then we just add these numbers up, and then we got 46, which is the answer. Well, can we do it reversely? The answer is yes. So I'm going to introduce two methods for this type of conversion. Let's come with the first method, which I called it comparison method. So imagine we have a number 42, and we want to convert this denary number into binary. Then what we are going to do is we first write the bit weight for each individual bit, starting from 1, and then got 1, 2, 4, 8, 16, 32, 64, 128. Then the next step is we are going to compare 42 to each bit of its value. So 42 is smaller than 128, so we write 0 for each bit. Well, why 0? Well, if we write a 1 here, the number will be at least 128, which 42 is definitely not, so it's 0. And then 64 is greater than 42, so 0 as well. And then 42 is greater than 32. So here comes an interesting thing. So here it should be 1 because 42 is larger. After writing a 1, the remaining terms, which is 42 minus 32, we have 10 here. So the next couple of bits, it will be composed, added up with a total of 10. Then we compare 16 to 10, we found 16 is larger, so we have 0. And then compare 10 with 8, which 10 is larger, so we have 1 here. And then minus 8, we have 2 remaining. Then compare 2 with 4, so we have 0. Then compare 2 with 2, we have 1, and we use it up, so the last bit is 0. Then we did it. The number 42 in denary is 101010 in binary. Then we come to another method which you can also use as well. So for the same number 42, we use short division. So 42 divided by 2, we have 21 and with a remainder of 0. Then we divide 21 by 2 again, which we have a quotient of 10 with a remainder of 1. And then we just repeat this step again and again until we reach 0 here. After reaching a 0, we just write the remainder in a reverse direction, starting from bottom to the top. So we have 101010, which is the corresponding binary of 42. It has the same result as the previous method, isn't it? You can check it yourself. Why does it work? Well, for 42, we can say 42 is equal to 42 times 1, which is exactly the same as 42 times 2 to the power of 0. Why we write it in this way? Because imagine we are thinking of, we put a single number on the last bit, which is the last digit, which has a bit weight of 2.2 to the power of 0 with a number 42. Then this is a corresponding binary. However, we know this is not the case because once it reaches the number 2, it has to increment by 1. So we are going to count how many 2's are there in the number 42. And then it turns out it's 21 2's. So we have here a quotient is 21, which is a carry bit increment to the next bit, with a remainder of 0, which means that nothing is left for this bit. So the last bit, we have 0 here. Then we convert it to this way, so we can write 42 is equal to 21 times 2 to the power of 1. Then we are going to see how many bits could be further incremented, because 21 is still larger than 1. So we divide 21 again by 2 here, which we have a quotient of 10 with a remainder of 1, which means that the carry 10 forward, and then there is 1 that can't be carried anymore, so it's left here. So the second bit is 1, and then it increment by 10. So which means that we can write it as 10 times 2 to the power of 2 plus 1 times 2 to the power of 1, and so on. So we just keep dividing by 2 to see how many bits it could be further incremented and what the remainder they are, and then just write them in the reverse order and got the answer. Well, you can feel free to choose this method. As long as it's work, the same result, it doesn't matter. However, if we only have binary, it could be causing us a headache. Well, we know that the Windows system is always crashing. Imagine one day you crash your laptop and you find these error codes, and you want to search it in the Microsoft community, which will be a headache for you to read these numbers. It's 0, 0, 1, 1, 1, 1, 1, how many ones, how many zeros? Well, people get headaches. So we invent hexadecimal for error displaying. So for the following picture is a Windows 7 error message with an error code showing up here. It starts with 0x, which indicates it's a type of hexadecimal number. So what is hexadecimal? Well, hexadecimal is a base 16 system. So as shown here, instead of base 2 or base 10, it's base 16, while the other properties are still the same. So with a 16 multiple between each successive digits. So for hexadecimal, the representation could be a bit annoying. So how to display a value that is greater than 9? Well, suppose we want to display a value 10 in Denary. Well, we want to display the corresponding value 10 in the hexadecimal. So first of all, somebody write a value 10 here, which there is a way to interpret it as 10 for one digit corresponding to 16 to the power of 0. But some people will have another interpretation as well. So it's split it into 2 digits. Say this bit is 16 to the power of 0 with a digit 0, and then 16 to the power of 1 with a digit 1. And then these are 2 completely different numbers. This is 10 and this is 16 in Denary. So this could cause confusion. Well, in order to solve this, smart humans invent another system. So they put a single digit 10 to use letter A. So if we write a letter A on this digit, which means that this letter corresponds to the last bit of this hexadecimal number, which has a weight of 16 to the power of 0, to make things clear. Well, we know 10 is A, then we can do the same thing for the corresponding number. So 11 is 12, oh, no, sorry, 11 is B, 12 is C, 13 is D, 14 is E, and 15 is F, and so on. So now we learned how the hexadecimal represents all the numbers. Then we are going to see how we can convert the hexadecimal number into Denary. Well, it's actually turned out to be quite simple. So suppose we have the largest 2-digit binary hexadecimal number, that is FF, and we want to convert it to Denary. So first of all, we write the bit weight of each individual bit. So it's 16 to the power of 0, then 16 to the power of 1. Then we multiply each bit with its bit weight, and then just add it up. So we have 15 times 16 plus 15 times 1. Then we have 255. So as we are talking about the largest number, now let's think about what is the largest number available for a 4-digit binary. It turned out to be very simple. The largest one, we just write 4 ones there, which if we add it up together, is 15 in Denary. Well, 15 is the same as the largest number available for a 1-digit hexadecimal. Is this a coincidence, or do they have a special connection? Well, we will see. This property will be especially useful when we try to convert a number from binary to hexadecimal. So as common with the previous slides, we know the 15 is the same as the largest number available for a 1-digit hexadecimal, which is f. So can we use a 1-digit hexadecimal to represent a 4-digit binary? Well, the answer is yes. So 2 to the power of 4 is 16, which means that if we have these binary numbers, so we have these ones, and each successive digits have a multiple of 2, then for a 1-digit hexadecimal, these numbers will have a multiple of 16, which is exactly the same. So we can see 4 bits here, and then times 2, times 2, times 2, times 2, so which comes to together. If we put it together, it's just 16. So which means that it is a true theory that we can use 1-digit hexadecimal to represent a 4-digit binary. So how are we going to use this property? Well, we can see here, for example, we have a binary value of 1011, and then we just convert it to the corresponding hexadecimal, added up 8 plus 2 plus 1, which is 11 in Denary, and we found a corresponding 11 number in hexadecimal, which is b. So we know this number is b in hexadecimal. Well, what will the things happen if we have more than 4 bits? Well, for example, 8 bits. Here we have 8 digits. So what we do is we just split it up into 4-bit groups. So it has 4 bits on the left and 4 bits on the right. Then we write the bit weight for the individual bits starting with 1 at the right-hand side, then to 8 on the left-hand side. Then we just add it up separately. So for the left-hand side group, we have 8 plus 2 plus 1, which is 11. Then we have b here. And for the right-hand side, it's quite simple. It's just 1. And then we just write this number together, which is b1. Well, you can verify yourself to see the b1, which is exactly the same binary number as this binary number. Well, after talking about binary to hexadecimal, we can do it another way around as well. So suppose we have a number in hexadecimal, we can use a very similar method to convert this number back to binary. So how are we going to do this? Well, it turns out it's kind of a reverse process. So suppose we have a number which is 3f, and the 3 we wanted to put it into a 4-digit binary. So we first put 4 digits here, which is 1, 2, 4, 8. Then we compare 3 with each of these individual numbers. So 3 is smaller than 8, we have 0. 3 is smaller than 4, we have 0. 3 is greater than 2, so we have 1. Then 3 minus 2, we have 1, so the last bit is 1. Well, for the right-hand side, we have f here. So the f corresponds 15 in Denary, and then we just convert this to the hexadecimal. So which is 1111, which is, then we have the answer. So 3f will change to 0011, 1111 in the binary representation. So here comes to be a bit of harder question. How can we convert a Denary number into hexadecimal? Well, we actually have already learned some of the methods, and we can use binary as an intermediate step between these two. So how are we going to do this? So let's see an example. Convert the Denary number 128 into hexadecimal. So the first step is to convert 128 into binary, which I'm using the comparison method here. We can see it has a bit 1 here, and then all the other is 0. And then for the step 2, we are going to convert this binary number into hexadecimal. So we group them by 4-bit, and then we will see the left-hand side 4-bit, which have a number of 8, and the right-hand side 4 bits has a number of 0. So we have 80. So 128 in Denary corresponds to 80 in hexadecimal. Well, here is something to give you a bit of additional thinking. Is there other ways to convert from Denary to hexadecimal? Well, if you figure out the way of how to do it, feel free to comment it below. Yeah, and we can just talk and discuss with other people while discovering new methods, which sounds really exciting. So this is the summary of this video, what we have explained so far. We say Denary is a human space system which has a base 10, and then binary is a computer system which has a base 2. Well, hexadecimal is to facilitate us to display the binary numbers for humans to get easier understand. So the hexadecimal starts with a base 16, and we need to know how to convert between these three number systems. And these are just brief slides showing how it can be done. Well, if you still have any questions, feel free to comment in the comment section below. And if you like my video, don't forget to give a thumb up and the subscribe button. Well, don't run away. There are 2 more exercises tailored for you. So here is the exercise 1, which dealing with Denary number and binary number. And here is the exercise 2, which dealing with binary number and hexadecimal number. Well, the answer to these questions will be released at the beginning of the next video. And hope you guys enjoy it, and see you guys in the next video. Bye!